Hello everyone, my name is Shihao and welcome to my poster presentation. I'm a junior in chemical engineering and my research is done under the guidance of Dr. Kristina Wagstrom in the Department of Chemical and Biomolecular Engineering. The title of my project is Designing a Portable Particulate Matter Monitor. Introduction. The goal of this project is to use a portable particulate matter sensor paired with the GPS coordinate data to map out the PM2.5 levels in the air. PM2.5 refers to tiny particles in the atmosphere that have a diameter less than 2.5 micrometers. Common sources of PM2.5 include power plants, forest fires, and vehicle emissions. Figure 1 shows other possible sources and types of PM2.5. Long-term inhalation of PM2.5 is dangerous because the particles are so small that it is capable of bypassing your body's defenses and enter deep into your lungs and even your bloodstream. This can lead to health problems such as heart attacks and strokes, which results in increased mortality rates. Materials. For this project, the particulate matter sensor I use is called AlphaSense OPC N2. This is a laser-based air quality sensor and it provides me data for the concentration of PM2.5 in the air. Figure 2 shows the sensor connected to its power bank. I also use Microsoft Excel for data entry and MATLAB, a coding language commonly used in engineering, for data processing. To obtain the GPS coordinate data, I use an iPhone app called Strava. The right side of Figure 3 shows the Strava interface. To produce the final graph of PM2.5 versus GPS coordinates, I use a tool called Retigo, or Real-Time Geospatial Data Viewer, developed by the EPA. The left side of Figure 3 shows an example graph in Retigo. Methodology. In this flowchart, I showed the steps I follow to obtain the final graph of PM2.5 versus GPS coordinates. First, I connect my sensor to the power bank, get the Strava app ready on my phone, and go on a walk to collect some data. Then, to obtain the GPS data, I download the GPX file from Strava's website, convert it to Excel readable format, and then extract the longitude and latitude from it. To obtain the PM2.5 data, I connect the sensor to my laptop and copy the PM2.5 data from the sensor file. I then put the GPS data and the PM2.5 data together into a new Excel file. After the new file is made, I run my MATLAB code, which reads the file, processes the data by doing averaging and trimming, and export the processed data into a new Excel sheet. Next, I reformat the outputted Excel sheet so that it fits the format requirements of Retigo. Then I upload the file onto Retigo and the graph is produced. This process is then repeated for new data collection. Key findings. Figure 4 shows the data collection run I did around lunchtime. This figure suggests that the PM2.5 level near a busy road is higher than the level of inner campus of UConn. The data points range is from 0, indicated by dark blue, to 2, indicated by deep red, in units of micrograms per meters cubed. Notice how the data points near Stores Road, which was full of traffic at the time of data collection, have higher values than those points within UConn campus. It's also important to note that this only shows a possible correlation of traffic and PM2.5 level, and to establish causation, more data needs to be collected and analyzed. Observations. This section is named Observations because these data were collected during times of poor air quality due to the western US wildfires. This means we can't really establish the correlation to any local air pollution source. Figure 5 shows a walk near an active construction site. Notice the range of the data starts at 24 instead of 0 compared to Figure 4, and caps at 41. This suggests a possible correlation between construction and increased levels of PM2.5 near the Jorgensen Center for the Performing Arts. Figure 6 is a continuation of the walk from Figure 5. However, it shows the exact opposite of what we expected. This figure shows the PM2.5 level is higher around inner campus and lower next to a busy road. This phenomenon can be explained by the fact that as time passed by, more particulate matters was deposited into the sample area, which makes sense because the end of the figure 5's range is about the same as the start of the figure 6's range, at around 36. It is also worth noting that at the end of this walk, the PM2.5 level reached a staggering 60 micrograms per meters cubed, which is very unhealthy even for the general population. Future goals. In the future, I would like to compare how different motions, such as walking versus running, affect the accuracy of the sensors. I want to determine a way to make the setup even more portable, which may involve 3D printing a custom case for the sensor in the power bank, and making a special box to put them in. I also want to take advantage of the portability of this setup to measure PM2.5 levels from different locations to gain more insight on what some local air pollution sources might be. Thanks for listening to my poster presentation. I hope you enjoyed. A special thanks to UConn McNair Scholar Program, especially to Dr. Renee Gilberti and all the graduate mentors for providing me this opportunity, and to my research mentor, Dr. Kristina Wagstrom, for guiding me through this project. Have a nice day.